Hey everyone, this is chapter 4, Modifying Pictures Using Loops of the Introduction to Computing and Programming in Python, a Multimedia Approach, the 4th edition. So to start, we're going to discuss the chapter learning goals. These goals include to understand how images are digitalized by taking advantage of limits in human vision, to identify different models for color, including RGB, the most common one for computers, to manipulate color values in pictures, like increasing or decreasing red values, to convert a color picture to grayscale using more than one method, and to negate a picture. The computer science goals for this chapter are to use a matrix representation to find pixels in a picture, to use the object's pictures and pixels, to use iteration with a for loop for changing the color values of pixels in a picture, to nest blocks of code within one another, to choose between having a function return a value and just providing a side effect, and to determine the scope of a variable name. So we perceive light different from how it actually is. So color is continuous. Visible light is in the wavelengths between 370 and 730 nanometers. And then you can see the decimal representation of that. But we perceive light with color sensors that peak around 425 nanometers for blue, 550 nanometers for green, and 560 nanometers for red. Our brain figures out which color is which by figuring out how much of each kind of sensor is responding. One implication, we perceive two kinds of orange, one that's spectral and one that's red plus yellow. It hits our color sensors just right. Dogs and other similar animals have only two kinds of sensors. They do see color, it's just less. So luminescence and color. So we perceive borders of things, motion, depth, via luminance. Luminance is not the amount of light, but our perception of the amount of light. We see blue as darker than red, even if it's the same amount of light. Much of our luminance perception is based on comparison to backgrounds, not raw values. And it's actually colorblind. Completely different part of the brain does that versus color. So digitalizing pictures is bunches of little dots. We digitalize pictures into a lot of little dots, and there's enough dots that it actually looks like a continuous whole to our eye. Our eye has a limited resolution, and our background depth acuity is particularly low. So each picture element is referred to as a pixel. So pixels are picture elements. Each pixel object knows its color. It also knows where it is in the picture. So for example, in this snippet of code, we create a file variable and we set that to a file path for a picture of a caterpillar. We say picture equals make picture, so we convert that file variable to a picture object, and then we type explore picture, and we actually are able to explore it. So let's try this as an example. Go here. All right, so what we're gonna do is in the command area, we're gonna say file equals pick a file. So we're gonna select a file, and let's go to here. Let's do week one assignment and let's do low picture. All right, so I got a file. Now I'm gonna say picture equals make picture and I convert that file. So now I have a picture object, right? I can see right here. So now I'm gonna type explore and I'm gonna actually see what this picture is. Awesome. So now what I can do is I can click anywhere in this picture. So let me click the eye of this lope, for example, right? I can see that the red is 55, the green's 27, the blue's 16. The color at the location is this color right here, this brownish color. And then this is 319 pixels over and 138 pixels down, right? And we can see that in any location. So we should see 0, 0 up here because that's close to the index, right? And then we can get our points similar to that all over the screen. So I'm going to close that. So hopefully you guys can do that example as well on your own computer. Um, Actually, in their example as well, they zoomed into over 500%, and then they can actually see the individual pixels as well on the picture. So a picture is actually a matrix of pixels. It's not a continuous line of elements. That is an array, right? A picture has two dimensions, width and height. And we need a two-dimensional array, which is a matrix. So you can see in the example on the bottom, that's a a 4 by 3 matrix. You can see four rows, um, sorry, 3 rows and 4 columns. So referencing a matrix, we talk about positions in a matrix as x, y, or horizontal, vertical, right? We go across and then we go down. So element 1, 0 in the matrix on the left side is the value 12. So we go over 1, or we go to column 1, and we go to row labeled as 0, which is 12. Element at 0, 2 instead is actually 6, right? So we're in the 0 column, which is horizontal, right? And then we look at the 2 column labeled, and which is vertical, so going down, and we see that in that location, that's 6. So encoding color. Each pixel encodes color at that position in the picture. So lots of encoding for color. Printers use CMYK, which is cyan, magenta, yellow, and black. Others use HSB, hue, saturation, and brightness, also called HSV, hue, saturation, and value. But we'll use the most common for computers, RGB. So encoding RGB. Each component color, red, green, and blue, is encoded as a single byte. Colors go from 000 to 255, 255, 255. If all three components are the same, the color is in grayscale. So 200, 200, 200 at 3, 1, as we can see in the matrix. 000 at position 3, 0. Or 255, 255, 255, which is white. So how much can we encode in 8 bits? Let's walk through it. So if we have 1 bit, we can represent 2 patterns, 0 and 1. If we have 2 bits, we can represent 4 patterns, 0, 0, 0, 1, 1, 0, and 1, 1. If we have 3 bits, we can represent 8 patterns. So the general rule in n bits is we can have 2 to the n patterns, right? So if we go back to the prior example, in n bits, so we have 1 bit above, and so I'm looking at is where it says if we have 1 bit, we can represent 2 patterns. So it's saying in n bits, you can have 2 to the n. So what we do is we say we have 1 bit, so 2 to the 1 is 2, and then gives us our 2 patterns. The next example says we have 2 bits. Well, 2 to the 2 is 4, so then we have 4 patterns. And then we have 3 bits. 2 to the 3 is 8. Then we have 8 patterns, and so on and so forth. So in 8 bits, we have 2 to the 8th patterns, or 256 different patterns. And if we make one pattern 0, then the highest value we can represent in our 2 to the 8th minus 1, or is 255. So is that enough? So we're representing color in 24 3 times 8 bits. That's 16,777,216, or 2 to the 24th possible colors. Our eye can discern millions of colors, so it's probably pretty close. But the real limitation is the physical devices. We don't get 16 million colors out of a monitor. Some graphic systems support 32 bits per pixel, maybe more pixels for color, or an additional 8 bits to represent 256 levels of translucence. So the size of images. So in this matrix, we can see different combinations. So a 320 by 240 image in 24-bit color, and then there's the number of bytes. And then we can see that the bigger the monitor resolution, and the higher the bits of color, the more bytes it takes for the size of the image itself. So a reminder, we're going to go back to manipulating pictures. So I kind of went through this example already, how we can pick a file, print out the file, make a picture, show a picture, and then print a picture. So I'm going to skip this example, but go through it and see if it makes sense to you, if you guys need a refresher from the previous chapter, and definitely try this out just to remember to yourself how to manipulate pictures and how to get pictures. So what is a picture? A picture is an encoding that represents an image. Knowing its height and width, knowing its file name, and knows its window if it's open via show and repainted with repaint. So how do we manipulate pixels? So there's a command called getPixel where you pass in the picture and you pass in the x and y value and it gets a single pixel. Similarly, we can say get pixels and you pass in the picture and it gets all of them in an array, square brackets in a standard array reference notation, which we'll generally not use. So I'm going to go through this example right quick. So let's here. So I already have the picture there. So let's say get pixels. I'm going to say picture, and then I'm going to say I want to see the index of 0. Cool. So this is my lope picture, right? And then I have red is 116, green is 186, and blue is 196. But let's just see what we already know, right? So we already checked prior. Let's check at 470, 124. Actually, I can't really do that. Actually, yeah, here. So I'm going to say get pixel, and it's not going to be an array. It's going to be a picture, and it's going to be, go back to this example, 470 and 124. So we're going to say 470, comma, 124. And let's see what our result is. 203, 231, 234. So we see 203, 231, 234, which is like this bluish color. I'm going to try to do get pixels. So one thing is because the bigger the picture you use, the more pixels, obviously. So you might even see JES crash in some instances. Now you can see that it's loading. It's going to output a massive array of every single color in this picture. Um, so it's going to be quite a bit of data coming back. So we'll wait for this to finish. While this loads, I'm going to switch back to the PowerPoint and we'll continue on. We'll check that in a second. So, and as you can see, you can grab the first object, which I went over in the example, where you can grab the square brackets of 0, and that's the very first object in this array. And then you can see the color of it, right? The red, the green, the blue, um, based on the picture that you have. So what can we do with a pixel? We can get the green, we can get the red, the green, and the blue, and they're all functions that take a pixel as input and return a value between 0 and 255. We can also set the red, green, and blue, and they're functions that take a pixel as an input and a value between 0 and 255. Let me check back on here. Still loading. All right, so we can also get, set, and make colors. For example, there's a function called getColor, which takes a pixel as an input and returns a color object with the color at that pixel. SetColor takes a pixel as an input and a color, then sets the pixel to that color. MakeColor takes red, green, and blue values in that order and make between 0 and 255 and returns a color object. PickAColor lets you use a color chooser and returns the chosen color. We also have functions that can make lighter and make lighter and make darker for an input color. So how do you find out what RGB values you have and where? We can use media tools. The media tools menu knows what variables you have in the command area that contains a picture. So we see open picture tool, we choose a picture to examine. So we can also use the explore, which explores our picture, like the example that we did. So how do we manipulate colors? So we can actually say um, print the color, get red at the pixel, set red. Um, let's go through this. All right, so I'm actually going to stop this because I don't know how long it's going to take. Let me actually close JES. So as you can see, it's not actually responding. Um, like I said, the bigger the picture, for sure, the more pixels that it has, obviously. Um, and things like this where it does actually crash your application for sure can happen. Um, so be conscious with that. And let's see if we can stop this. JES end task. Looks like it's gone. All right, so while that does its thing, let's continue. So go through these examples where you can set color, and these are all functions that you'll find in the the tools inside JES. But we can also change pixels directly. So in this example, they create a file variable with the direct file path, and they make a picture out of that file. Then they show the picture, and then they actually get a pixel at a certain location, and then they actually set the color to yellow. And then they repaint the picture at the end to show this yellow line. So you can see where the arrow's pointing that there's this yellow line showing up on this picture of this random woman. But that's really dull and boring to change each pixel at a time. Is there a better way? For sure, we can use a loop. So our first picture recipe. So we're going to decrease red. So let me go back to JES because it's kind of needed now. Still not responding. Let's see if we can open a new version. So while that closes, hopefully this opens. And again, you might run into these similar problems. So let's just use this JES window for now. And let's try to write this function. Oops. So we're gonna go to here. So we're gonna write a function called decrease red that takes a picture. It goes to the pixels. It changes each value or each pixel. It gets the red value, and then it decreases it by 0.5. Okay. So what we'll do. So we're gonna define a function called decrease red, and it takes in a picture or an input called picture, right? And then we say let's just say for p in get pixels of the picture. And then we're going to say set, oops, back real quick. We're going to say set red, yep, set red. And we're going to say we need p. And then their example has the value, which is get red at p times 0.5. So we're going to say get red at p times 0.5. I think I'm missing. Nope, that's good. So see, I'll double check the parentheses to make sure that they're all lined up and they all have an equivalent on each side. And then we're actually gonna, so let's actually let's load this program. I'm gonna save this as test, like I always do. Okay, so now let's load it. It's not loaded yet. All right, so it's loaded. So now I'm gonna say, let's just say picture equals make picture pick a file like that. So now I'm going to go to my location, week 1. I want the lope picture. Come on. Lope picture. Awesome. So now if I look at picture, it tells me the path, it tells me the height, it tells me the width. So now I can actually call my function called decrease red, and I pass it this picture. Cool. So that actually worked. But one thing that didn't happen is I missed something, right? Now I need to actually show the picture after I need to repaint the picture after I do that. So now let me call repaint picture. And you can actually see here. So let me actually show the picture first. Let's see if this shows the original. Um, Hold on. Explore picture. So actually, I actually changed my picture variable. So let me go to picture. Let me reload the lope picture again. Okay, so now here you can see that the colors are normal, right? These are the colors that we would expect. But now again, I'll call decrease red. So you'll see as it's running, it takes the red, it goes through every pixel and it takes the red out. And then once we explore that again, we can see that it's obviously quite different than what it was prior. So here's before, and then here's our after with the red that's decreased. So let me close these. Okay. So this function is pretty easy to understand. So it defines a function like we've been doing. It takes an input, which is picture. And then it says for p in get pixels. So for every single pixel, right, we're going through this array or this matrix of pixels for the picture. So every single pixel we're going to go through, and then we're going to set the red. And let's look at what set red does. Set red takes a pixel and a red value. So our pixel is p, right, because we're going to get every single pixel. And then the red value is the current value of the red times 0.5. So we're decreasing the red amount by half. Okay, so I'm going to close that. continue on. Okay, so our first picture recipe works for any picture. So as you can see, they did the same thing, and they have a decreased red for this picture of this child as well. So continuing, um, you can use it in, here there's an example of how they used the same function decrease red for this picture as well, just like we did. So how do you make an omelet, right? Here's a random question. Something to do with eggs, right? What do you do with each of the eggs? And then what do you do? So all useful recipes involve repetition. Take 4 eggs and crack them. Beat the eggs until. We need these repetitions or iterations to construct in computer algorithms as well. So decreasing the red in a picture. So here's the recipe, right? It's to decrease the red. The ingredients, a picture, and then name it pick, right? Step 1. Get all the pixels for pick, and then for each pixel p in the set of pixels, there's our example. And then step 2, get the value of red of pixel p and set it to 50% of its original value. We use a for loop for this. Our first picture recipe. So like I explained, um, we define decrease red and it passes in a picture object. All pixels is a variable which equals get pixels of the object that you pass in, pick. And then for p in all pixels, so it goes through this massive array depending on what file or what picture you pick. And then we have inside the for loop, right? We can see that box around there. Note the indentation. The value equals get red, so we're getting the red at each pixel, assigning it to a variable called value. And then we're going to call the function set red, which takes in the pixel p, and then we multiply the value times 0.5 to get 50% of the original value. So how for loops are written? For is the name of the command. So we see for p in all pixels, right? An index variable is used to hold each of the different values of a sequence. The word in. So we can see for p in all pixels. So we're saying for um, you could say for the chip for each chip in the bag of chips, right? You know, you're saying each object, and you're saying what the container object of it is, which is in this case we have each pixel p in the list of all pixels. A function that generates a sequence. The index variable will be the name for one value in the sequence each time through the loop. Then we have a colon, and then a block, the indented line of code. So the for object in object container. That's a standard for loop and how it is traditionally written. Um, it's you'll definitely use it a lot as you go through more complex code and more difficult things. So a for loop is useful for sure. So what happens when a for loop is executed? The index variable, which is p previously, is set to an item in the sequence. The block is executed. The variable is often used inside the block. Then execution loops to the for statement, where the index variable gets set to the next item in the sequence. Repeats until every value in the sequence was used. So what this is saying is, say I have 10 values in all pixels. So I say for value 1, I do my thing with value 1 as p, right? Then I do value 2 with value 2 as p. And I continue and continue and continue until I get through every object. And then I'm done with that indented block of code with that for loop. And then I move on to the next step. I already went through there. So get pixels returns a sequence of pixels. Each pixel knows its color and place in the original picture. You can change the pixel, you can change the picture. So the loops here assign the index variable p to each pixel in the um, picture one at a time. So here we can see how we decrease red, and then the example how we did it prior in the command area. You don't actually have to say all pixels, you can just get the pixels directly because get pixels returns a sequence of pixels. So in the top one, we have a variable all pixels, which is the returned array of get pixels, or we can just use that directly like in the bottom example. So do we need the variable original red? No. So having removed all pixels, we can also do that without original red in the same way. We can calculate the original amount right when we are ready to change it. It's a matter of programming style, but the meanings are exactly the same. So this is how we did the example previously as well. We say for p and get pixels, and we say set red at the pixel. We get the red amount from the p, which is the pixel. We multiply it by zero point 0.5. So I think we already walked through this pretty slowly. Um, I'll just go through this quickly. Um, we get all the pixels from the picture, then we make p be the name of each one at a time. We get the red value from pixel p and name it original red. And then we set red value of pixel p times 50% original red. Then move on to the next one. You can see in the bottom example, it moved on to the next pixel. Change it. And then we go from the left to the right. So tracing, stepping, walking through the program. What we just did is called stepping or walking through the program. You consider each step of the program in the order that the computer will execute it. You consider what exactly would happen. You write down what values each variable name has at each point. It's one of the most important debugging skills you can have, and everyone has to do a lot of debugging, especially at first. So once we make it work for one picture, it'll work for any picture. So as you can see, we can pass in any of these pictures below, and it does the same thing. So think about what we just did. Did we change the program at all between each of our examples? No. Did it work for all the different examples? Yeah. What was the input variable picture each time then? It was the value of whatever picture we provided as the input. So if you have a variable picture in your command area, that's not the same as the picture in decrease red. So what this is actually saying, let's go to our JES. I think this is not the right one. Sorry. We're going to go to here. So what it's saying is that the picture here inside this decrease red is not the same as this picture here, right? They're two separate scopes, and we'll learn about more about scopes soon. So we read it as a recipe, which we already did that as well. So let's use something with known red to manipulate. So here's a picture of Santa Claus, and we can use the exact same function, and we can totally remove the red. So as you can see in this example, they actually ran this decrease red function twice, and it actually removed 50%, and then it removed another 50% as well. So if you make something like write picture to picture and then file name, sorry, if you make something you like, so then once you make something, you can actually export that picture to a certain file location. So let's go back to JES. We can see in JES functions there should be files, and then there should be, sorry, there should be pictures, and there should be write picture to. Um, the picture is the picture you want to be written out to a file, and then the path is the path to the file you want the picture written to. So it takes a picture and a file name, and then it writes the picture to the file as a JPEG, PNG, or bitmap. And be sure to end the file name in JPEG, PNG, or bitmap for operating systems to understand it. So then you can see an example right here. They pass in a picture object. They write the file to this temp location, or sorry, they create a temp location, and then they actually write the file to that temp location. Um, be sure you end your file in JPEG like we just said, and if you don't specify a full path, will be saved in the same directory as where JES is. So what about increasing the red? So we already did the decrease here, but what about how do we increase? Um, so we modify our function to multiply by a number higher than 100% or 1.0, as you can see in their example. And because they increased it, the really red parts of the picture are actually going to um, look odd, like in this example. So remember, if you're questioning why did this happen to this lady's face, you can remember that the limit for redness is 255, and if you go beyond 255, all kinds of weird things can happen if you have modulo checked in options. So as you can see, here's JES options, pixel color values by 256, and you can see it there. So how does increase red differ than decrease red? Well, it does increase rather than decrease, but other than that, it takes the same input. It can also work for any picture. It's a specification of a process that will work for any picture. There's nothing specific to a specific picture here. So we can clear the blue. So what this does is this function clear blue goes through every pixel and it sets blue of each pixel to 0. So let's try this example out. So what we want to do is we want to set let's call this clear red, and we're going to set the red pixel to 0. Right? So for every pixel, we're going to set red at the pixel. We're going to set it to 0. So let's load this. Let's explore the picture to see what it looks like. So we already decreased the red in this example, but now we're going to actually remove the red. So it's going to be called clear red. It's going to take the picture. It's doing its thing. It's done. Now we're going to explore the picture. Let's see what it looks like. Awesome. So the prior example wasn't too far off, but now let's try. So because it doesn't look too different because it was already kind of cleared from the reducing it by 50%. So let's clear the blue instead. So I'm going to load this function. We're going to call clear blue, and we're going to pass it the picture object. So that's done. Awesome. So now we set the red values to 0 and everything. We set the blue values to 0 for everything. So now all we have is a green, just different shades of green for this picture, this antelope. Now you might be questioning, well, can we clear the green too? Well, for sure. Let's try that. So let's clear the green. We're going to set that all to 0. We're going to load it. We're going to do clear green, pass it the picture. Now it's going through every single one. And now we have black, right? We learned previously that 0, 0, 0 was black, right? And we set everything to 0. So you can see that we have everything as black. Awesome. So we could also do like this, 255, and we're expecting we should see white. It's going to be called the same picture name or same function name. It should be called set white or something, but we'll keep it like this for now. Explore the picture. So now we only have green, right? So what happened, right? We were expecting white, weren't we? Well, in this example, we only set the green to 255. But what if we wanted to set all of them, right? So let's do set blue, P 255, and let's do set red, P 255. So you can see we're going to use the same P for each of these methods. It's all inside the same for loop, so it's going to be the same P. And we're going to set blue, green, and red all to 255. So we're going to load it, we're going to run it, and then we're going to explore it once it's done. And we have a white picture, right? All pixels at every location are 255. Awesome. So let's continue with the PowerPoint. So how many bytes are in a 1024 by 768 image? So let's do some math. So let's go to here. 1024 times 768. And here we have 786,432. So I'm going to go back to here. And I see that's my number one option there. So which one of the below pictures was generated from this function? Define change to, it's a function. It takes a picture object as an input, and it says 4 pixels and get pixels, or 4 pixel and get pixels. It sets blue at each pixel to 0. So which one do you think is the right one? So from the original on top to the bottom one. So we could definitely try this out. Um, we know for sure it's probably not number 2 because we can see that there's actually maybe an increase of blue. We can see that it's probably not number 4 because that's more of a yellowy. So I would think that would be an increase. So it's probably either 1 or 3. So we're setting the blue to 0. I would actually probably say it's more likely to be number 1 as the answer. So now what happens if we set the green and we increase the green by 2 times? Now in that case, we'll probably likely see number 3 as the output of this function. But again, take a picture, increase it, and see if you can kind of match and correspond something similar. So can we combine these? Why not? So how do we turn this beach scene into a sunset? What happens at first? At first, I tried to increase the red, but that made things like red specks in the sand really prominent. And that can't be how it really works. But here's a new theory. The sun sets, less blue and green is visible, which makes things look more red. So what we can do in this example is instead of changing the red to make it more red, we actually just decrease the blue and the green a little bit. So the red's not so prominent, but the blue and the green are faded, so it does look more like an actual sunset would look. So you can run through this example with a picture, find a picture of a sunset and do something similar. So how do we lighten and darken an image? So we can write a function called lighten, which takes a picture object. Again, we use a for loop for the for in um, structure for a for loop. We grab the color at each pixel, and then we actually make lighter that color object, and then we set the color of that pixel to the new color object that we have. And then we can do the same thing for darkening as well. So let's try that in our example. So we're going to say define a function called darken image, takes in a picture. Let's call it pic. Okay. We're going to say for p in pic, and then we're going to say I think we had to get the color right. Yeah, we have to get the color at the pixel. Get color p, and then we have to say make lighter for that color. But we know that get color returns the color, so why can't we just say make lighter, get color, and then we're actually going to say set color at the pixel. So we can all combine this in one cool line. So we're going to say set the color at the pixel, make it lighter, and update it. So we're going to, oh, sorry. This is actually dumb. So this is something that you want to make sure you don't do. I defined a function called darken image, but I actually called make lighter. So actually, let's call this make darker instead, which makes more sense. So we're going to load the program. Awesome, it loaded perfectly fine. We're going to let's get our picture again. So we're going to say picture equals pick a file. Awesome. We're going to pick the little picture, but my picture is not quite a picture yet. We're going to say picture equals make picture, and we're going to pass in the picture. It's cool. So now I updated my variable picture, which was a string path to the file. I updated that with the new picture object. So now I'm going to say darken image, and I'm going to pass it the picture object that I just created. So here's an example of an error that I have. So it says an attempt was made to call a function with a parameter of an invalid type. This means you did something such as trying to pass a string or method that is expecting an integer. So it doesn't like a picture object. Let's see. Oh, okay. So if you can see what we did, or if you already knew and you already fixed it the right way before I did it, we actually want to get the pixels right for the picture object. So let's load this function again. Let's make our picture. Oops. So I actually, no, I did something dumb again. So I tried to call make picture of picture, but I already had it as a picture object. So picture, if I look at just print out picture, it's a picture at the file name. So I already have it as a picture. So if I call make picture again, it's expecting a string. It's not going to get a string, so it has a picture object. So that's fine. So now we're going to call our method that we tried to call originally. We're going to call darken image. We're going to call it with the picture. And again, wow, another error. So we're going to actually say get pixels, right? Again, this is great troubleshooting for you. I make mistakes. I'm not perfect in my programming as well. So hopefully the errors that I'm getting, you guys, I hope you I hope you guys get these errors as well, so you guys can learn from them similarly. Just be conscious as you do the programming that everyone makes mistakes and everyone has these errors. So you're definitely not alone. Even your instructor for this course is making mistakes as he goes as well. So this finally worked, right? We troubleshooted our program. We got everything working fine. We ran our function darken image against the picture object that we created, and that worked okay. So now let's actually explore this picture and see what our output is going to be. Awesome. So we actually can see that this is quite a darker antelope. than the original. So we have a whole bunch of different antelope options here. I'm going to close this example as well. So now let's run darken image one more time, and let's see if we can get even darker. All right, awesome. So it does look a little darker as well. If we're questioning what make darker actually does, oops. I don't actually know if it's defined here. Um, make darker. Okay. So you pass in the color you want, and it returns the new darker color. Takes in the color and returns a much darker version of it by calling make darker 3 times. So this example, they say make much darker, and they call make darker, which passes in the color that make darker returns, which patches in the color make darker returns, which returns the make darker color of the first color that they pass in. So kind of a weird example, but it just shows that you can call make darker quite a few times and get a result that you're looking for. So creating a negative, let's think it through. So RGB goes from 0 to 255. Let's say 10, or so let's say red is 10. That's very light red. So what's the opposite? That's lots of red. So the negative of that would be 245, which is 255 our max minus 10. So for each pixel, we negate each color component in creating a new color. So we negate the whole picture. So you can see this example here, right? So now they go through, they get the red, green, and blue, they negate the color, and then they set the color. So let's try this example. So we're going to define a function called um, negate pic. Takes in an object or input called picture. We're going to say for p in get pixels of the picture, and then we're going to say, let's say set color, and we're going to say p. We're going to say make color. We're going to say 255 minus the get red of p. We're going to say 255 minus the green of p. And we're going to say 255 minus the get blue of p. Awesome. So what we did is we combined quite a few lines of code here. They make a color, which is 255 minus red, green, and blue, and they call that negative color, right, or negate color. They set the color with pixel, comma, negative color, or yes, negative color. And then they create, so they have a lot of variables in here that really aren't necessary because I did the exact same thing in one line. So let's load the program. It looks like I'm missing a parenthesis. So we have one that goes to there, one that goes to there. That's good. Okay, we just need one more. Awesome. So that's cool. We save it. It worked fine. So now we're gonna say, let's negate this picture and pass in the picture object. It's running, it's doing its thing. It's negating this picture pixel by pixel, going through each step. That finished. Now we're gonna explore this. Awesome. So now our antelope that we're seeing here looks a little evil, looks kind of scary, and it's definitely the negative of the picture that we once had. And again, didn't follow the book example. We optimized the code, we improved it, we created less variables, we made it one line of code to negate an entire picture of an antelope that we had prior. So as you can see, original, negative, and then negative, negative, which turns it close. Looks a little bit different than the original, but it's pretty close to it. So converting to grayscale. So we know that if red equals green equals blue, we got gray. But what value do we set all three to? We need what we need is a value representing the darkness of the color. There are a lot of ways of getting it, but one way that works reasonably well is dirt simple. Simply take the average, right? So the average of three things in this example, red, green, and blue, we just add those up and we divide by 3. So converting to grayscale, we go through each object and we make a color, which is the intensity of each red, green, and blue divided by 3, and we can get the gray for that color. So can we get it back again? Nope. So we lost that information. We no longer know the ratios between the reds, the greens, and the blues, and we no longer would know any particular value, right? Because we took the average and we kind of made some assumptions. But that's not really the best grayscale. In reality, we don't perceive red, green, and blue as equal in their amounts of luminescence. How bright or non-bright something is. We tend to see blue as darker and red as brighter, even if physically the same amount of light is coming off of each. Photoshop's grayscale is very nice, very similar to the way that our eyes see it. Black and white TVs are also pretty good. So building a better grayscale. We'll weigh red, green, and blue based on how light we perceive them to be, based on laboratory experiments. So in this example, we can see that we're multiplying each object by some proprietary numbers, right, to decrease. And it looks like those values, which they should, all add up to 100. And then we set the color for our new and improved grayscale. And then you can see the comparing the two grayscales, the average one is on the left and the weighted one is on the right, which does for sure look more realistic uh, to the actual picture that we once saw. So let's use a black cat to compare. As you can see, the left is our average one and the right is the weighted one. So prior picture, sorry, here's the original. And then as you can see on the right, the weighted. So a different sunset generation function. So we can call make sunset 2, which reduces blue and reduces green. But in but instead of doing all the make sunset functionality, we actually call two additional functions. One called reduce blue, which goes through all the pixels in the picture, and they set the blue value to 70% of what it was. Then we call the reduce green, which goes through every pixel as well, and also reduces each one by zero point 0.7. So the thing does the exact same thing as it did earlier. It's easier to read and understand. To make a sunset is to reduce blue and to reduce green. So we use hierarchical decomposition to break down the problem. This version is less efficient, but that's okay, right? And you might ask, why is it less efficient, right? Prior, we were going through all the pixels in the picture. So uh, let's just say we went through 100,000 pixels, for example. Prior, we went through 100,000 pixels one time, and we made two changes. We set the blue and the green to different amounts. Now, we're reducing the blue, so we're going through 100,000 pixels one time. Then we're reducing the green. Now we're going through 100,000 pixels again. So in the end of this, instead of going through 100,000 pixels that we were once going through as an example, now we're going through 200,000 pixels. So that's why it's definitely less efficient in that example. But programs are written for people, not computers. So if it's easier to read for you, go ahead and fill your programs with functions, a ton of functions. So let's talk about functions. How can we use variables like picture in both a function and in a command area? Why do we write the functions like this? What ways would be just as good? Is there such a thing as better or worse functions? Why don't we just build in calls to pick a file and make picture? One and only one thing. We write functions as we do to make them general and reusable. Programmers hate to have to rewrite something they've written before. They write functions in a general way so they can be applied and used in many circumstances. What makes a function general and thus reusable? The reusable function does one and only one thing. Contrast these two programs, right? On the left side, we can see our make sunset program where we change the blue and the green. And then on the right side, we can see a make sunset program, which calls reduce blue and which calls the reduce green functions. Yes, they do the exact same thing, but make sunset uh, and make sunset sum pick, where it takes in an object called sum pick, works the same in both cases as well. So observations on the new make sunset function. It's okay to have more than one function in the same program area and file. Make some sunset is this one is somewhat easier to read. It's clear what it does, reduce blue and reduce green. And that's important. Programs are written for people, again, and not computers. So your variable names should make sense to you. Your function names should make sense to you. The complexity of your function should make sense to you, right? You're writing it for yourself. It's going to do what you want it to do, and the computer is going to execute it as long as it's in the proper syntax. But as far as variable names, function names, complexity, it's written for people, for programmers, not for the computers. So we consider variations. We can only do this because reduce blue and reduce green only do one thing. If we put pick a file and make a picture in them, we'd have to pick a file twice, better be the same file, and we make the picture, then save the picture so that the next one could get it. Does make sunset do one and only one thing? Yes, but it's a higher level, more abstract thing. It's built on low it's built on a low level one and one, only one thing. We call this hierarchical decomposition. You have something that you want the computer to do. You refine that thing in terms of smaller things, and then you repeat until you know how to write the smaller things. Then write the larger things in terms of smaller things. Are all the things named picture the same? So what if we use this? Uh, what if we use this like this in the command area? So what if we said file equals pick a file? We turn that file into a picture. We say make sunset and we pass it the picture, and then we say show sunset and we pass it a picture. I want to increase the blue of every pixel by 25%. I write this. What goes in that example underneath get blue? Do we say set blue 0.25 times b? Do we say set blue pixel? So we're increasing, right? So we know it's not going to be a smaller number. So we can remove option 1 and 3. And we're going to increase it by 125% or 175%. Um, so if we multiply, so think about it. So if we set the blue color, so let's go back. So get blue of pixel returns the blue amount 0 to 255 of the pixel. So if we multiply that by 1, right, it's going to be just the same number that it was. So what we really need to do is multiply it by 1.25, right? Because 1 is 100% or the exact same thing. And then we want to increase it by 25%. So 1.25 is the same object plus 0.25, which is 25%. So our actual answer for this example of what goes here is set blue pixel, comma 1.25 times b, or option 2. So I want to increase the red of each pixel by the same amount. I write this. For pixel and get pixels, pick r equals get red, and then I give it the pixel. And then what do I actually do? So I want to increase the red of all pixels by the same amount. Do I subtract 50? Do I divide by 50? Do I multiply by 50? Or do I add 50? So we're going to say we want to increase it by the same amount. We're increasing it. So we can do the bottom one, option 4, which is adds 50 to every number in the pixels. So what happens when we use a function? When we type in the command area make sunset picture, whatever object is in the command area variable picture becomes the value in the placeholder input variable picture, right? So if we have in the command area a variable called picture and we pass it into the make sunset function, the picture inside there is totally different, right? It's another, it fills that placeholder. So make sunset's picture is then passed as input to reduce blue and reduce green, but their input variables are completely different from make sunset's pictures. For the life of the functions, they are the same values, picture objects. Names have context. In natural language, the same word has different meanings depending on context. I'm going to fly to Vegas. Would you please swat that fly? A function is its own context. Input variables, placeholders, take on the value of the input values only for the life of the function, only while it's executing. Variables defined within a function also only exist within the context of that function. The context of a function is also called its scope. Input variables are placeholders. Think of the input variable as a placeholder. It takes the place of the input object. During the time that the function is executing, the placeholder variable stands for the input object. When we modify the placeholder by changing its pixels with set red, we actually change the input object. Variables within functions stay within the functions. The variable value in decreased red is created within the scope of decreased red. that means that it's only executing while decrease red is executing. It only exists while decrease red is executing. If we tried to print value after running decrease red, it would only work. It would work only if we already had a variable defined in the command area. The name value within decrease red doesn't exist outside of that function. We call that a local variable. So in this example on the right side, we define a function called decrease red, which has an input called picture. And then that's where picture in this example is the placeholder, right? We call decrease red with a picture object. That picture object exists outside the scope of this decrease red function. And the input that we give it, we use that through the scope inside of the decrease red function. The scope continues with in the for loop. For example, the P is only accessible inside the indented block of the for loop. So after the for loop breaks and we try to call the variable P, it's not really going to do anything because it's not inside that actual same scope. So writing real functions. Functions in the mathematics scene or sense takes input and usually returns an output, like ord or make picture. What if you create something inside a function that you want to get back to the command area? You can actually return it. We'll talk more about return later. That's how functions output something. But consider these two functions. We have decrease red. We go through each pixel. We set the value of we get the value of the red value of each pixel, and then we set the red by 0.5% on the left side. On the right side, we actually set the red. We do value times an amount. First, it's perfectly okay to have multiple inputs in a file or in a function. So we can see on the left side we only have one input. The right side we have two inputs: picture and amount. The new decrease red takes an input of the multiplier for the red value, right? So if we call decrease red 0.5, it would do the same thing. But if we call decrease red picture 1.25, it would actually increase the red by 25%. So names are important. This function should probably be called change red because that's what it does, right? It doesn't just decrease the red because you could put a big number in there as well. Is it more general? Yes. But is it the one and only thing that needs to be done? If not, then it may be less understandable. You can be too general. Understandability comes first. Consider these two functions below. They do the exact same thing. The one on the right looks like the other increase decrease functions we've written. That may make it more understandable for you to write first, but later it doesn't make much sense to you. Why multiply by 0 when the result is always 0? Right? So in the on the left side, we want to clear the blue. So we want to set all the blue to 0. The left side just sets it to 0. The right side does some complexity, right, which gets the value of blue and then multiplies that value by 0. Well, we know in math that anything times 0 equals 0, so why waste time with that when on the left side we can get it done just as easy? Always write the program understandable first. Write your functions so that you can understand them first. Get your program running. Then make them better. Make them more understandable to others. Set to 0 rather than multiply by 0. Another programmer, or you in maybe 6 months, may not remember or be thinking about increase and decrease functions. Make them more efficient. The new version of Make Sunset takes twice as long as the first version because it changes all the pixels 2 times. Specifying pixels by index. Decrease red. So we can also, we used range previously in an example. So we can also go through each pixel. We can grab the pixel at the index value, and we can do the exact same thing that we did previously. But instead of getting a for object in, um, where we're actually getting the pixel, this is actually going for index in range from 0 to the length of the pixels, and it's returning the index instead. So you can try to decrease the red indexed version instead. It does something similar like we saw prior. So just half of the picture decreased red. Um, so what we did here, we do for index in range 0 to the length of pixels divided by 2, right? That's half of the picture. Right? So if we have 100,000 pixels, we do divide by 2. We're only covering 50,000 pixels, so the first 50,000 pixels are the ones that actually get affected. So what if you wanted to copy half to the bottom half? So what we can do is we have a function called copy half. It takes in a picture um, object. We get the pixels for that picture. We iterate through all of the pixels in half of the picture, and then we say we want to be at the index plus the length of pixels divided by 2. So we're as we go through, we're actually repeating the exact same thing um, on the bottom half of the pixels as well, or bottom half of the picture as well. So definitely try this out. Try out this example. You could do something with these tiki heads like they did in this example, but just test it out. See if you understand. Do go through, step through the program. Make sure that you understand and can explain what each line of code is actually doing and why it's actually doing it, and maybe it'll actually help. So consider this program. Which picture did this generate? Which picture below did this generate? So we make an empty picture, right? That's our first line, and we get all the pixels in the picture. So then we say for I in the range, length pixels divided by 4. So we're going to cover a fourth of the picture. We're going to say set the color to red. Then we're going to say for I in 3 times the length of pixels divided by 4, and then the length of pixels. So we're going to start farther down, right? And then we're going to set the color to red as well. So we should see the answer should be, I believe that it is number 1, where we cover the top half and the bottom half. So mirroring. So in this example, we write a function called mirror half. We takes the picture object, does our normal get pixels. Our target is the length of pixels minus 1. Then we go through the length divided by 2, so we're only going to get the top half of the pixels. We go through each pixel. We assign that to variable called pixel 1. We get variable called pixel 2, which is at the target, right? And the target is the length of pixels minus 1. So that starts from the bottom. So the target's starting from the very last pixel, and then the index is starting from the very first pixel, and then they're actually going to go through. Target's decreasing, index is increasing, and they're going to actually go through, and they're going to make a mirrored picture like we have above. So given what we've now learned from getPixels and the order of pixels, predict the behavior of this program. So clear red on half. So we get all the pixels, we go through half of the pixels, we get the pixel at a certain index, and then we set the red color to 0 for that. So is it going to clear red on the top half, the bottom half, the left half, or the right half? So we know from the prior examples that it's going to actually clear it on the top half. So number 1 is the correct answer. So that's all that this chapter includes. We did a lot of manipulation of pictures. We did a lot of different examples using for loops. We learned some stuff about writing functions, how to write good variable names, how to create smart function names. We did a ton of different things. So definitely take some time to go through these examples, read the book, read the chapters, and make sure they all make sense as well. And if you have any questions, as always, please feel free to let me know. Thanks, guys.